Hello everyone, welcome to this video on field theory. In this video we shall see finite extension of a finite extension is a finite extension. That means suppose we have three fields, say f, e and k, and they are contained in each other. That means e is the extension of this field f and k is the extension of this field e, right? And this extension e over f, that means is a finite extension. That means this degree of e over f, that is finite, and the degree of k over e, that is also finite. That means this is also a finite extension. Then they are saying the extension field k, which is defined over an extension of f, this is also finite. That means the degree of k when taken over f, that is also finite. So this result says that let f, which is contained in e, which is contained in k, these are the fields, and they are saying if this extension k over e is finite, the extension e over f is finite, then the extension k over f is also finite. Moreover, this extension, the degree of this extension k over f, so this thing, the extension of k over f, that is equal to the degree of extension k over e multiplied by that of extension e over f. So this is the result. So let us prove this. This is a very simple result to prove. So for that we have given this degree to be finite. So let us call it m, and we have also given the degree of extension e over f to be finite. So let us call this as n. So you also know that any extension field over a given field that acts as a vector space over the given field. So this k, this act as a vector space, treating the scalars, taking the scalars from this field E. Thus we can talk about the basis of this field k over E, and what is the degree of this field extension, that is equal to m. So we have m such elements. So let us call them by v1, v2 up to vm. Similarly, you can say that E is a vector space over f, and we have its dimension as n. Therefore we have n such elements present in the basis of E over f. So this is given to us. We have just assumed these numbers. Now we need to show that the degree of k over f is also finite. So let us try to take an element from this field k. So let this u, it belongs to k. Then we can write this k, because k has basis elements v1, v2 up to vm. So we can write the element u as a linear combination of its basis elements. So this is by virtue of the property of vector space. So we have written it over these basis elements. So that would be summation I varying from 1 to n, because we have total. So it would be a1 v1 plus a2 v2 up to am vn, because in total we have m elements and the degree is m, right? And these a1, a2, am, they are from E. They belongs to E. So now again E is an extension field of f. That means we can again write these ai elements as the linear combination of the basis elements of E, because E is again a vector space over f, and taking these scalars now from f. So these bij's, they belongs to f, right? So we can substitute this value of ai from here to here. So let us see what do we get. So we have u is equal to summation I varies from 1 to m as such, and the value of ai, that would simply be equal to this thing. So that is what we have written over here into vi, right? Into vi. So we have this thing. So now the element that you started with from k, you have written that element as a linear combination of these elements. And how many such elements are there? Because we have I varying from 1 to m, j varying from 1 to n. So vi, wj, that are total mn elements. These are total mn elements. So you have written your k as a linear combination of mn elements, where these constants, they are from f. So you have written an element as a linear combination of these elements, these mn elements, and where the coefficients are taken from f. So that means you get a generating set of mn elements. So you can say that the degree of k over f, that would be at most m, because this generating set may also contain these mn elements. They may also contain some elements which are dependent on each other. So in order to get any linearly independent set out of this, you have to shrink this set. So at most we have mn elements. So the degree of k over f should either be equal to mn, or it should be less than that, equal to that. But moreover, this mn is a finite number, so we can say its degree is finite. So we are done with the first part. So first part says that the finite extension of a finite extension is a finite extension. So this is a finite extension. So now, to prove the second part, what we have to prove, we have shown here that this set viwj, where I varies from 1 to m and j varies from 1 to n, consisting of mn elements, that forms a generating set. That forms a generating set of this k over f. Now in order to show that this is a basis set, we only have to show that these elements, they are linearly independent to each other. If that is the case, we would have the basis for k over f. So these elements should be linearly independent. For proving the linear independence, what we do, linear independence of this basis is viwj, where I varies from 1 to n and j varies from 1 to n. To prove the linear independence of k over f, we must take the scalars from f. So that's what we have done. We have taken the linear combination of these elements and we have took these scalars from f, and we have written these linear combination as equal to 0. Now in order to prove the linear dependence, if these constants, these bij's, they come out to be 0, in that case we can say that the vectors vi, wj, they are linearly independent. So proceeding further, this is the expression that we have with us. So we can rearrange the terms. We can just commute these two, because now we are in field and these elements are in k. So we can use the commutativity and associativity. So we can just commute and take the brackets over these two and call this whole term as some ci for I varying from 1 to m. So these ci, they belong where? Now can you see this thing? It becomes summation I varies from 1 to m, some ci and into multiplied by vi. Now these vi's, we have assumed them to be the basis vectors for k over e. So they are in k. So these basis vectors, they are in k, and these constants ci, they are in e. Why they are in e? Because they are written as the linear combinations of the elements wj, which is the basis of e. So these are in e. So we got a linear combination of vectors vi, which forms and these vi's vectors, they form the basis for k over f, k over e, right? And because these form basis, that means they should be linearly independent. That means these ci, they should be equal to 0. this is because it is given that this ki has basis vectors as vi. So vi is a basis vector of k over e. That means the ci's are 0, and what is the value of ci? That is equal to summation j varying from 1 to n bij wj, that is equal to 0. So these linear combination is equal to 0. Now you see these wj's, they were the basis for e when you take their linear combination and taking the scalars from f. These bij's belongs to f. How? Because that's how we have defined them from here, like in the last step, right? So we have wj's, they are in e, we have bij's, they are in f, and the linear combination is equal to 0. Because wj, they form the basis for e, that means each of these constants bij, that is equal to 0. So we got bij as equal to 0. Now if you got bij's as equal to 0, we have considered this linear combination, and and this linear combination is equal to 0. It implies all these bij's, they are equal to 0. It implies that the set vi wj, that is linearly independent. If this is linearly independent, so it forms a basis for k over f. And how many such elements are there in this basis set? We have I varying from 1 to m and j varying from 1 to n. So in total we have n elements in it. And what was m? M was the degree of k over e, and what was n? N was the degree of e over f. Thus we have reached at our result that we intended to prove. So this was quite a easy proof. I hope you got the point. Well, that is it for this video. Thank you for watching.